Yeah, so it should be recording. So I guess I'll just do a brief introduction. So um, Joonho Lee is a PhD candidate at the Robotic Systems Lab, and he works on ANYmal learning. So as you can see in the pictures, and yeah, so I guess take it away.
Yeah, thanks for the introduction. Oh, wait, somehow, can you hear me clearly? Somehow
Yes.
it's echoing.
Oh, yeah, sorry, let me mute.
Okay. So yeah, thanks for the introduction and thanks for the invitation. So today I'm going to talk about our recent work where we applied RL to develop a locomotion controller for this quadrupedal robot. The robot is called ANYmal. And in this work, we trained the neural network policy in simulation, like over the simulated rough terrains. And we tested it over many different natural terrains, which are almost impossible to simulate. And our policy generalized very well to different terrain shapes and different terrain properties. So yeah, we somehow achieved the state-of-the-art performance in this rough terrain. So as you can see, we actually went hiking with this robot last summer, and yeah, it slips a lot and the terrain is like super random. But yeah, as you can see here, it can adapt very well to different slopes and different kind of friction coefficient. And yeah, this kind of hiking was not possible with the best model-based controller we had. So yeah, it was quite an achievement. So I'll talk about the motivation behind this work and some technical details on how we did it. So let me first give you some context on what's happening in the Lego robotics. So there are actually many super nice Lego robots out there which are commercialized, and they are controlled by like conventional method, like model-based or optimization-based method. So whenever we talk about this Lego locomotion, the question we always get is like, why are you trying to solve something that Boston Dynamics already solved? Like, why are you trying to get something that's like, oh, wait. Yeah, why are you trying to develop yet another locomotion controller while we have this very nice model-based controller? So yeah, this is partially true. Like they can do many amazing things, but I believe that this is still an open problem and there's a big challenge behind it. And yeah, data-driven method like deep learning can make a breakthrough. So let me first briefly explain what's happening in these conventional controllers. So to make this robot walk, actually making this robot walking around is quite a difficult problem because the robot has to balance itself and it has to follow where we command it to go. And it also has to reject disturbances and like, yeah, something there can be many different tasks. So to do this online on this robot, conventional methods usually rely on this optimization, like solving optimization problems. And like if you want to solve that online on this small robot, like on this using this small CPU in this robot, you have to somehow simplify the dynamics a lot because the robot, like when we walk, we make a lot of contacts and with this kind of discrete interaction with the terrain and the contact dynamics itself is very hard to model. And if this mathematical model becomes too complex, we cannot solve it online on this robot. So we usually make several assumptions, like we define this kind of gait pattern by hand, and we make assumptions like the contact only occurs at the feet. Because if you want to consider the other kind of contact, like, for example, if you walk over like rough terrain, we might hit the knee, but it's hard to model all kinds of different contact interactions because it makes the model much more complex. And the terrain is usually like assumed to be static and planar around the robot to further simplify the problem. And yeah, this kind of like reduced model usually works very well in many environments where we deploy these robots, like well-known robots. But the problem is there are some situations where these assumptions break and where this conventional method loses robustness. For example, if you take the robot to the forest, like the terrain is like soft and the foot slips all the time. So this is a model-based controller running there. So as it slips all the time, and as it cannot have a like very nice foothold there, it at the end it completely loses balance. So this guy is holding it so that it doesn't roll over. And as we assume that the contact only occurs at the feet, if there's a tree branch or something hanging in the leg, it also like, yeah, freaks out like this. These kind of things might happen if you take the robot to some unknown environment. And yeah, for one more example, if the terrain is dynamic like this, you can see that controller can easily diverge. So yeah, there are many corner cases like this. And yeah, there are many well-known corner cases like this. And
Can I ask a question?
Yeah.
So this is basically a problem with the controller and not with the perception of the terrain, right?
Yeah.
Okay, so there's no way to have an extra sensor to perceive the terrain so that your controller does better.
Yeah.
Okay.
Yeah, but yeah, the controller I show you here are blind, so they are basically relying only on the joint states and the IMU of the base. So,
right,
yeah.
but if you had, let's say, some sort of a LiDAR or some radar, short distance radar, that would be better.
Yeah, we can improve that, but there's still a lot of like tricks going there, even if we have the perceptive locomotion, because like the sensor measurements are like inherently, like it always has noise there, right? Mm-hmm. And when it walks over the terrain, it might have like undesirable contacts happening. And yeah, that's what I'm going to explain in the next slide. And yeah, so there can be this many corner cases, and usually what people solve these corner cases are adding some reactive control modules. This is a like block diagram from a controller from a well-known lab. And this is ANYmal also has the similar structure there. So you can see many reflex or recovery modules. So for example, for this step reflex, for example, like when the robot walks over the terrain, sometimes like it makes undesirable contacts like here. So like when a foot gets stuck in this kind of small obstacles, if you can't react to it like directly, like immediately, the robot might fall over. And there can be this, even if you have the perception, there can be error of the perceived terrain and the model inside. So this kind of foot trapping can easily happen. And how people usually solve is there's kind of detection rule inside, so based on the leg face. And when it detects that, when it knows that it has some undesirable contact, they usually add some different motion primitives like this, or add another constraint in the optimization problem. So in this conventional paradigm, though, I think this is the only way, like how we can handle such an like undesirable interaction with the terrain. And if you engineer that super well, like Boston Dynamics, then at the end you will get a very robust controller. But it is usually very difficult to imagine what will happen and what kind of foot-terrain interaction will happen and what kind of corner case will there be. Yeah, the problem is here, like if you take the robot outside in this kind of terrain, it gets stuck and slip together, or if you take the robot to this water like stream, then there's like constant disturbance to the legs and it might hit the knee on the rock, or yeah, there can be many different corner cases happening. And if you want to overcome these kind of corner cases, then we have to come up with a very, very nice mathematical model that can cover all these corner cases, or you should be able to imagine what kind of things will happen. And yeah, you have to come up with like reflex modules to cover them. But this is usually very difficult. And yeah, that's why we are interested in using RL or like other deep learning method for control. I like to control this guy. Yeah, because deep learning is basically good at like distinguishing different patterns. So yeah, we started using RL to like generate motions for this quadrupedal robot from this paper, like published in 2019. So what we did here was we wanted to do RL for this leg robot, but it is usually very expensive to actually run the reinforcement learning algorithms on the robot, right? you have to do some random exploration, but then you might break the robot, which is very costly. So what we did is we first developed a rigid body simulator, which can simulate the robot quite fast, like which can simulate any articulated system like this. And what we did was we just trained it in the simulation and ran it on the robot. But what happens is usually like this, so this is so-called reality gap. And the reason why it happened is that the actual dynamics of the real robot is very different from the robot model in the simulator. Because if you see these actuators of the robot, they have so many components. They have harmonic drives and springs, and there are some frictions coming from the ceiling. So this kind of nonlinear dynamics is very hard to model. And many model-based controllers, they just ignore this nonlinear dynamics of the actuators. But as we are training the policy in simulation, we had to somehow take this into account. So what we did was we collected some data from the robot, by actually doing this, and we tried to excite many different frequencies of the actuator and simulate some impact. It's quite funny. So, and we trained this actuator network and put it in the simulation. And yeah, at the end, we could get a quite realistic simulator where we can train a policy there. So at the end, we developed this accurate simulation, and then we trained policy using deep reinforcement learning algorithm. We used TRPO there, and we try to replace all this optimization stuff with a single neural network. And and the result was pretty nice. So yeah, so we could train different behaviors very easily without making any assumptions on contact or something like that. And cool thing about this behavior is when the robot rolls over the ground, it actually makes a lot of contact with the ground. And this kind of complex interaction with the terrain is usually very difficult if you want to handle this with the model-based method, because you have to somehow schedule where the robot will make contact and what kind of body part will hit the ground, something like that. But it's cool that we can just do it by making a good simulator and by running a model-free reinforcement learning method. So yeah, in this work, we got this nice simulation tool. So yeah, we were very happy with this, and we hope that we can just randomize the terrain, and if we just train it there, then we will get a nice locomotion policy. So what we did is we made some rough terrains in simulation, like these three, and we applied some random disturbances to the base and some random friction coefficient, and trained this guy by giving reward if it follows the command direction and penalize if it falls over.
So question.
Yeah.
When you simulate random terrains, do you also account for softness and deformable terrains, or do you assume that if you give it enough shapes, it's gonna account for any deformation?
So we were in the latter direction. So in our simulation, actually, we were only able to simulate the rigid terrains. Yeah. So that's actually an interesting part of this work, because we only trained in the rigid terrain, but it actually was able to robustly generalize to different terrains. And so we hope that by randomizing a lot, different shapes and applying different disturbances, it would adapt to different situations. So yeah, basically we used rigid terrains.
Got it. So the other question is, you had now you have a policy which works really well, and you also have a dynamics model. Do you also worry about issues of stability or proving stability of the underlying closed loop system?
No, we didn't look into that actually theoretically.
Okay.
Yeah.
Cool. Thanks.
Yeah. So yeah, but if you just train it end-to-end in random terrains, you usually don't get a nice locomotion behavior. For example, if you just randomize the slopes and train this guy, it just shakes all the time like this, and it doesn't really adapt to slope, or it just does this jumpy behavior and like hope for the best if it like, and it can just luckily go over this kind of obstacle. So the problem is the task itself is a partially observable MDP, because like to the controller, the observation is like the observation that the policy gets is basically some low level states from the state estimator from the robot. So we know the base velocity, base orientation, and a short history, and we gave short history of joint states, like joint position, joint velocity, and joint tracking errors. And if you want to walk, actually, there can be many hidden states, right? Like, for example, like imagine yourself walking, you should be able to know that your foot is touching the ground or not, or your foot is slipping or not, or if you are going uphill or downhill. But if we just naively train this guy end to end, it seemed like it couldn't get this kind of hidden information from this observation. Like looking at this kind of behavior, it doesn't really adapt to slope. So we had to like make some change in our training pipeline. So and there can be, I think, 3 solutions. First one is to increase the data a lot and hope for the best. The second is actually changing the observation space. We can just include one of these hidden states in the observation, then it might get better. The third will be like not doing RL or changing some training method. So we tried the second one. So we tried adding the context states into the observation, because like in almost all the Lego robots, there is a context state estimator inside. So we can actually get this directly from the robot. And this is quite a strong feature like that's used for other controllers. So if we add this context states in the observation and let it train, actually the behavior is much more consistent, and yeah, it actually looks like walking, right? It gets much better. But the problem is if you run it on the system, the estimate, like you can see that the robot shakes a lot, right? Can you hear that? And it makes very unhealthy noise. So the thing is, the estimator in the estimated context states are usually not very clean as we get in the simulation. And like we can like think of a way to somehow randomize the noise in the simulation, but then it leads to like failing training. So like adding this extra like explicit intermediate representation was also very difficult. And a bigger problem was that if you want to, like, we can add this kind of different features to the observation, like foot context state or foot slip state or whatever we can estimate from the like robot state. But the problem is we don't know what's really important for the locomotion. Like I couldn't find any like scientific research on what states are really important for walking. That's the bigger problem. So what we tried to do in this paper was we stacked this time series of this proprioceptive measurements, like by proprioceptive measurement, I mean the joint states and the ANYmal state. We collect the history of this guy and give it to a temporal convolutional network, which is a convolution, like basically a 1D convolutional network applied on this like time axis.
So I have a question. What are the sensors on ANYmal? As in, when you say proprioceptive state, how many ANYmals, and do you have force sensors, and where do you have force sensors and accelerometers or any sort of contact?
So yeah, there's no contact sensor. And what we have is we have an ANYmal in the base. And for each joint, we can measure joint position and joint torque. And from joint position, we can like estimate joint velocity. So in this work, I used joint position, joint velocity, and the joint position tracking error. So I didn't use the torque, but yeah, you can also use the joint torque measurement.
Of course. And then a single ANYmal in the base is sufficient, or do you have multiples to handle drift and other stuff?
We have single ANYmal. Okay. Yeah.
Got it.
So yeah, the basic idea was to extract some information from this history of proprioceptive measurement and learn some intermediate representation there to to make it walk, like to learn some nice features that's important for locomotion. And yeah, another problem is that I think if you have some experience with using some standard RL algorithms like PPO or TRPO on LSTM or CNN networks, it's usually pretty difficult to train them. The thing is, when the network gets bigger and like when you use more complex architectures, if you just try to tune PPO there or TRPO there, it's very difficult. Like they are usually very sensitive to hyperparameters, and they very easily converge to like local minimas, like the behavior shown before. So yeah, we also had to apply some other techniques to make this training faster and much better.
Sorry,
so
So how did you ensure that the outputs of the TRPO policy would be in the, I guess, would be low energy for your robot?
So in this work, we actually didn't care about energy consumption. What we cared about is the traversability. What we wanted to achieve was to climb over different terrains. So yeah, we penalized the joint torque during the training, no joint velocity. But yeah, we didn't care about energy that much in this work. Yeah, because
And how long was the sequence of states that you were giving to the TCN?
Here we used 2 seconds of measurement, and the measurements were taken every 0.02 seconds. Yeah.
Right. So actually reasonably long, like not just like frame stacking, like 3 frames, like actually, yeah, that's interesting. Thanks.
Yeah. So yeah, so to train this guy well, we had to introduce 2 more tricks, or 2 more techniques. The first one is called learning by cheating, like the method, we call it privilege training. So it's from this paper called learning by cheating. So what they did is, so they were trying to solve this autonomous driving problem in this color simulator. And if you usually just do the imitation learning with this image input, it's not very working well. So what they did is they first trained a privileged agent given a low-level states of the simulator. So this agent knows where the other cars are and what's the color of the traffic light and so on. And as this agent knows everything, it learns super fast and it performs super well. And then they imitate this guy, like using this guy. And by imitating the behavior of the privileged agent, this guy learns to extract this kind of important features from the RGB image. And they claim that they achieved 100% success rate in some benchmark task in the color simulator. And this is actually something we can apply to our task, because we also have a simulator where we can get the nice states related to context. And what we want to train is a bigger network that will learn on the robot, but that doesn't have this direct access to this kind of state. So what we did is basically, we first train a teacher policy using TRPO, and we just gave whatever contact related states we can get from the simulation. So we added contact state, contact forces, and some terrain profile around the fit and friction coefficient and disturbances to the base. And as this guy knows the noiseless states from the simulation, it learns actually pretty fast. So we usually trained it for 8 hours, and then it learns to adapt to different situations. And then just like the learning by cheating, we train this TCN policy to imitate this guy. And one last question was, we have these randomized terrains generated by some noise, parameterized noise, but it's hard to define what range of terrain parameters to use during the training. The thing is, if it's too flat, then it will overfit to this flat terrain, and it will not it will fail to go over rough terrains. And if the terrain is too complex, too difficult, then it will not get much reward, and it will just learn some conservative behavior and not really walk. So what we did is we defined like some kind of performance measure of each terrain. So we called it traversability. So this is kind of success rate of traversing the terrain. So when the robot can walk over a certain velocity, then we say it's success in the terrain. And this is like success rate in the terrain. And as you can see here, in this flat terrain, success rate is high. And in this rock terrain, success rate is low. And what we want to do during the training is we want to provide the agent with the terrains with this mid-range traversability, because the terrain shouldn't be too easy and it shouldn't be too difficult. So what we did is we sampled different terrain parameters and we picked the terrain parameters with this mid-range traversability and tried to keep track of these parameters using particle filter, which is basically evolutionary algorithm. And yeah, with this strategy, we could somehow automate the introduction of the terrain during the training. And yeah, you can see that the training, like the terrain gets like continuously more difficult as the agent learns to walk. So yeah, this was the last source. And yeah, and then we could get a nice locomotion controller, and we tested it over many different kind of terrains. And as I said before, like we only trained it in the rigid terrain, and yeah, it could still generalize to different environments, like different terrains on the snow, and like even when the terrain is dynamic, it could actually adapt very well because control frequency is super fast and it already experiences many different shapes of the terrain during the training. So yeah, and to show you some nice behaviors learned from RL. So I mentioned the foot tracking reflex before. So to do this in this conventional approach, you had to somehow handcraft this kind of rules and motion primitives. One good thing is, as we just train in using like model-free RL, this kind of behavior actually just emerges. So as it hits with this step, it actually lifts the front leg higher to overcome it. And yeah, and as we randomize the terrain friction a lot, so this controller could also adapt like very well on the slippery terrain. So we put this whiteboard here and pour water here, so it was very slippery. And yeah, as soon as the robot slips, this guy changes the walking frequency. It actually walks faster, like steps faster to adapt to the slippery terrain. And we could drive the robot in any direction on this slippery, like whiteboard. And this kind of like slip recovery was only possible before using like additional modules, like additional contact detection module and some motion primitives. This controller had that kind of modules, but yeah, it didn't freak out that much, but still was not able to like fully recover from this slippery terrain. Yeah, this is one of the model-based slip recovery controller. This was also cool. And so during the training, we actually don't do the domain randomization, but we apply some random disturbances to the base, like to the body. And this random disturbance is known to the teacher policy. And yeah, and the robot is about like 40 kilograms. We added like 10 kilograms of weight, but it could still do the same thing with this weight, and it could stably like walk over different obstacles and like in many different directions. But if you do the same thing to the model-based controller, it usually like fails completely. Like if it doesn't have any like disturbance observer or some other modules. So here we commanded 0 velocity to the model-based controller. And yeah, you can see that it's somehow drifting forward. And yeah, the controller gets super robust. So this was also a nice result. And lastly, yeah.
Yeah. Were you randomizing? Yeah, I had a question. Were you randomizing the shank length and the mass of the bodies in the robot and stuff like that during training?
In this work we didn't do that. So I actually tried with like with this like dynamics randomization and without this dynamics randomization, and we couldn't see a big difference. But adding the big disturbance to the base was actually helpful. But yeah, we didn't like randomize the inertia or like length because we have pretty nice CAD model, right? So I just didn't do that, and there was no big difference.
I see. Yep.
Yeah.
Thanks.
And yeah, one cool outcome was that there was a team like going to DARPA Subterranean Challenge last year, and they used our controller instead of this model-based controller, and it was quite an achievement because like when you talk to robotics guy, they usually like when we talk about this using neural network controller, what they usually say is it's a black box. No one knows what's happening there. It's dangerous, so they don't use it. But yeah, in this case, they tried our controller and it was much more robust in many other situations, like when they were testing. So yeah, at the end, they just took our controller there. And these stairs here, we never introduced this kind of super high stairs during the training. And I actually didn't expect this guy to work here, but yeah, they just deployed it there. And yeah, the robot survived. At the end, the robot fell over because of some internal problem, but yeah, it could still traverse this kind of challenging terrain. So yeah, before finishing the result, yeah, I want to show you some like simple benchmarks to verify why I needed these 3 ingredients. So firstly, what I did was I tried to reconstruct this privilege information from the intermediate like output of the TCN. So I just trained another decoder that like reconstructs this terrain elevation, terrain normal, or friction coefficient. And we observed what happened when it hits the step. And the cool thing is when a leg gets stuck, like when a foot gets stuck there, these red spheres or red ellipsoids are the estimated terrain elevation. And the size of the ellipsoid is the like variance, like the uncertainty output. So you can see that in this latent representation, it encodes that there's something in front of the robot. And it expects that the terrain is rough, like by this uncertainty. You can tell that by this uncertainty as soon as it hits the step. And even after it overcomes the step, this uncertainty is like stay high because it like from the history of last 2 seconds, it can expect that the terrain in front of the robot will be rough. And yeah, we could also reconstruct the friction coefficient when it's walking over the slippery terrain. And it shows some reasonable values. Like on the rubber pad, it's like 0.75 or something. And on the slippery part, it goes down to 0.2. And then it recovers when it starts walking over the normal terrain. And yeah, having longer history actually helped. So we had these 3 benchmark tasks in the simulation. One is for the slope and one is the step. And we varied the step height and measured the success rate. And the last one is we applied the external force and saw the deviation of the trajectory. And TCN1, TCN20, TCN100 means the number of the time step. And as you can see here over the steps, it usually, in general, it gets better when it has higher, like when it can observe higher, like longer history, which makes sense. And cool thing is that like when we go over this high step, actually the success rate of the front legs and hind leg was different. Like what happens here is that when the history is short, it doesn't adapt the behavior of the hind leg, like the leg in the behind. But when we have this like long enough history, it can actually adapt the hind leg too, such that it can overcome it better. And of course, it adapts better to the external force. And
just a question from the chat. Martin French asks, for extreme elevations like a high curb, does the controller try to jump on it?
So this guy is basically blind. it only has access to the measurement from the joint and the base state. So when there's some big obstacle in front of it, it just gets stuck there. But it tries to like lift the front leg higher, but as it cannot see the obstacle in front, it's, yeah, for now it cannot jump over. Yeah.
Thanks.
Yeah, that's something we want to solve later. And like privileged training was actually very helpful for training. Like I tried to train this TCN without privileged training using TRPO or PPO, but I couldn't make it actually walk with the same reward function. That's why I put 0 here. And it usually just converges to this local minima where it just falls over to the like command direction. But with the privileged training, like the success rate or like all the performance was much better. And the curriculum learning was also very helpful. It could still work without the curriculum learning. But the thing is, without the curriculum, the agent experiences many too difficult terrains at the beginning of the training, and which leads to the like highly conservative behaviors. So you can see here, the agent struggles with this step. Like if you just train it without curriculum, like by just uniformly randomizing the train parameters. But with the curriculum learning, the behavior was much more aggressive, and yeah, the overall traversability was much higher. So yeah, I'm a big fan of curriculum learning. But yeah, so this was very helpful. Yeah, that's all from my side. And yeah, to conclude, yeah, we tried not to use any handcrafted intermediate representations like contact state or foot slip states, which are commonly used in Lego robotics, but still using this TCN and some nice training pipeline, we could achieve the state-of-the-art performance in rough terrain. And like, as I said before, we only simulated the rigid terrain, right? And one cool observation here is that maybe we don't need accurate simulation of the complex physical world. If we have like maybe some simplified like representation of the soft terrain, or like, yeah, if we can train a controller that can generalize well to different situations, maybe we can do the same thing like without simulating the complex physical world. Yeah, it was just interesting observation. And now we have this know-how, and like we have some data, like now we have this training pipeline now. So we are, as a follow-up work, we are working on the perceptive locomotion. So now we attach LiDARs, and we are trying to use sensors to actually more actively go over the obstacles. Maybe the robot is too heavy to jump over it, but it can at least predict the obstacle and lift higher. This is something we are working on. And during this work, we went so many different places in the Switzerland. Like we went hiking, or we went to cave, or like many other places. And during the experiments, we collected some image data from the onboard camera and some trajectory data from the robot. So we have like this bunch of unlabeled data. So what we are trying to do these days is to like make some visual navigation system using this like data. And also some people are trying to like implement similar controller to other platforms like ANYmal on wheels or some excavator in our lab. Yeah, that's all from my side. Thank you.
This is wonderful. First of all, you have excellent graphics and excellent videos. I guess the advantage of working on some of these systems. Any questions from people? I think Martin had a question. No, actually, I guess it was answered.
Yeah,
I had Martin.
Yeah, sorry. Go on. No, I just was saying.
Okay, sure. So one question I had was, what sort of stuff do you have for visual? You said you are moving towards perceptual sort of sensing. What sort of stuff do you have in terms of sensing? What sensors are you using, and what modalities are you hoping to cover?
So we basically have 4 rear senses on the robot. So we have RGBD data, and like usually that depth measurement from the rear sense is very noisy. So what we do these days is to attach LiDAR. Here it's a dome LiDAR. So we have two dome LiDARs in the front and back, and we have this Velodyne LiDAR, like this disc-like one here. And yeah, for now we only have these ones. But we can also attach RGB camera somewhere here. And the other joint measurement. That's already perception we have.
Okay. In terms of perception, so you said real sense is very noisy, but LiDAR gives you sort of, do you look very far ahead, or do you only need to look, let's say, the next 3 or 5 time steps? When you do footstep planning, right? How are you planning this?
Yeah, for locomotion, we only care about like somewhere near the robot. Like when I train this privilege in like policy, teacher policy, I only use these little scan points around the foot. Yeah, so for only locomotion, we don't look that far. And what we are planning to do is to have another higher level navigation system that can actually look farther. But for locomotion, locomotion level, I think we don't need to look that far.
What is the frequency with which you have to sort of close the feedback loop for locomotion?
In this work, it was 50 Hertz.
Is 50 Hertz not too low, or do you think it's completely sufficient even for super dynamic stuff like slipping and stuff?
I think in our case, it was sufficient. Like 50 Hertz is already like super fast. Like you can compute 50 times a second.
No, of course I know what 50 Hertz means, but okay.
Yeah, we also tried higher like control frequency, but somehow we are gradually lowering it, because like when the control frequency is lower, like when you run this like when you collect data in this longer like temporal like this abstraction, it learns faster actually. If you have this shorter time step, it learns faster.
Yeah, because the RL becomes easier. You can see farther out.
Yeah.
Did you also? Yeah, go ahead, Florian.
So suppose you were not just doing locomotion on a challenging terrain, but suppose you wanted to do more acrobatic stuff, like the robot standing on its 2 hind legs, or jumping, or doing things like this. Would you follow the same training strategy?
So yeah, we are also interested in that kind of thing, acrobatic stuff. But for that, we first need to have a very light and dynamic robot. But our robot is more for like stability. So it's like our robot is not that fast. So maybe we'll need a different robot. And if I want to make a learning system for that, I might have to think about other approach, because like to do backflip or like some, maybe if you want to jump over different stepping stones, you have to plan much further, right? So yeah, I guess we need to somehow think of a higher level optimization loop and some tracking using maybe RL-based controller. But like I wouldn't do it like this, because it doesn't look that far.
I guess one acrobatic, but perhaps not very generally useful thing, but maybe useful for a demo thing that you can do with this type of robot, which is meant to be stable, is have the robot on skates and try to have a model of the skates as well as the robot, and try to see how fast the robot can go on this skateboard. Would you do the same thing you did here for that type of scenario?
So it's not exactly the skate, but we have this similar system here, like ANYmal with the wheels. And yeah, we can actually just skating is it requires pretty short horizon to think of, right? So yeah, we actually just try to learn it in the same way, but with a different model. It was actually okay.
Cool.
So I have questions. When you do locomotion, what sort of, so you, as I think Ian Florian kind of was asking, the gates that you have are locally stable. Have you also looked at, like, let's say, bounding gates or running gates? What happens, or what are special considerations for those kind of things?
Yeah, so actually discovering different gait is very difficult thing to do if I just train it like this, because it always converges to trotting, because like it can track the command velocity like the best.
Easily.
Yeah, easily.
But when you do learning, you never sort of specify gaits. A gait emerges, or you specify trotting.
Here I just randomize the leg phase, and I just let it learn, and then
so the timing of the phase is also learned.
Yeah.
Okay.
So it always converges to trot, but yeah, I also want to see other gaits, because in some situations other gait might be more optimal, right? So I actually tried to learn a higher level policy that outputs the gait pattern, something like that. But it was usually very hard. So I didn't get any successful result yet. But yeah, that's something we will have to explore for sure, because there can be many different combinations. Like with this method, I think it will always converge to trot, like with this reward function.
So then when you are thinking of like, so I've seen videos of ANYmal on wheels, and particularly that is very impressive to me from a form factor perspective. I'm very curious, how do you design, let's say, behaviors, such as ANYmal on wheels walking stairs? Like, so the wheel thing needs to sort of roll up to the stairs, then needs to go up and then sort of go beyond. So I'm curious, how are such behaviors designed, and what part of that is learned versus like hard control?
So for now, like the existing works out there using ANYmal on wheels, they use the trajectory optimization to go over the steps. So yeah, we haven't explored that much using RL in that direction. We just started, but yeah, so I'm not sure.
Okay.
But yeah.
I actually have a quick question about, like, because you're training the policy by imitation, right? Like, you don't do any fine tuning on it, or do you?
I actually tried fine tuning it with PPO or TRPO, but yeah, the gain was not that big. And if you want to do another RL on this big network, then it requires a lot of parameter tuning, hyperparameter tuning. You need to tune the learning rate and batch size, all of that. So I was losing more than gaining. So now I'm just doing the imitation learning. But the initial idea for this project was to actually imitate and then fine tune it. But at the end, I just didn't do it.
Yeah, because like I guess the reason I asked is, like, you would think that given that it has strictly less information than the teacher policy, it might not be optimal given the information that it has. But yeah, it seems that from what you were saying, it actually is able to estimate fairly well, like, and get the same information. That's interesting.
Yeah. So yeah, our higher priority was to make something that's working on the robot and to make something that we can use out there. So yeah, we didn't want to like tune too much there.
So maybe a follow-up question to this is, of course, not many others have access to ANYmal, at least for research. One, the platform is super expensive. Two, as you said, it breaks very often. Now you have antibiotics, and not everybody does. But do you have, let's say, these environments and the baseline controllers included in, let's say, a simulation environment? So a lot of people who would want to do this can do this, but like not on the real robot, but at least on a simulator in a setup.
So yeah, the simulation for ANYmal is there, but like the one from the ANYbotics is only given to the buyers.
I'll sell people.
Yeah, as far as I know. But you can, like, I actually open sourced the controller I developed in this work. So maybe I think it was here. So here I actually implemented the simulation for this ANYmal using RiSim. So maybe you can take a look at the, maybe you can use this RiSim simulator instead of the simulator from the ANYbotics.
Oh, ANYbotics people use a different physics engine?
Yeah.
Okay.
Yeah.
So I have a question.
I believe there was one last question from Morrison French. I don't know if he's messaged me and said he had a question.
Yeah, hello. Can you guys hear me?
Yes.
Yes.
Okay, excellent. Yeah. So I just want to say that was a fantastic presentation and really eye-opening in terms of the utility of RL. My question is just in regards to situations, essentially where we have terrain that's like not traversable at all. For example, say walking on thin ice. Like as a human, we know that we shouldn't step onto certain sections of ice because we can feel that the force isn't responding back to us properly.
Yeah.
I was wondering if there'd be ways to encode that within the simulation.
Oh. I think you will have to be creative to do that, but in this simulation, like maybe you can define some region the robot cannot enter and you can give penalty there. But yeah, I don't know, like we cannot simulate breaking ice, right? And like if you want to make the robot don't go to like fire or don't walk over the ice, I think we will have to use real world data for that. Like we maybe try to walk over only the safe region and do the anomaly detection, or like we can try walking over this ice actually and make use of that data to prevent the robot to go there at the higher level. But in the simulation, yeah, maybe not. Maybe there's no clear way to actually simulate that, like visually and physically.
I see. Thank you.
Cool. So I think that's probably it. Like that's the it's 11:30. So I believe I don't know if Nishkrit sent you the email that like we have some like meeting slots with like students from the lab now. I don't think you have the link, so I can send you that. But yeah, just to make sure you're available. Yeah, I'll just send you the link to that. It's another Zoom meeting.
Okay. So do I have to go to this room now?
Yeah. Yeah.
Okay. Okay. Thanks. Thanks for coming.
Thanks, everyone.
Thank you.
Bye.
Bye.